Professor Wang is the chair professor of computational intelligence in the Department of Computer Science and the School of Data Science at the University of Hong Kong. Prior to this position, he held various academic positions at the Dalian University of Technology, Case Western Reserve University, University of North Dakota, and the Chinese University of Hong Kong. He received a Bachelor of Science degree in electric engineering and a Master of Science degree from the Dalian University of Technology and his PhD degree from Case Western Reserve University. He is also the editor-in-chief of the IEEE Transactions on Cybernetics. He is an IEEE Life Fellow, IAPR Fellow, and a full member of Academia European. He is also a recipient of the APNNA Outstanding Achievement Award, IEEE CIS, Neural Networks Pioneer Award, and the IEEE SMCS Nobel Winner Award, among other distinctions. So without further ado, let's welcome Professor Jun Wang, please.
Can you see the screen? Okay. All right. Okay. Thank you for the introduction. It's my pleasure to be here, share with you some work we have done recently. Okay. This morning and that's 2 days already. Many speakers talk about optimization. I don't have to stress the importance of optimization. Okay. Let me go straight forward. Okay. I will concentrate on the recurrent neural networks. Okay, which is with feedback connection in network structure. It's more like a human brain. Basically, we know our human brain is a nonlinear, a very complex nonlinear dynamic system. Our neuron are from birth to death, always active. You know, when we're thinking, we're doing some decision making, the neural highly activated. So this dynamic process, we want to model it mathematically or physically. Okay, using recurrent networks. So this recurrent network should be globally convergent to the optimal solution if you have some decision to make, or at least stable in a sense, not isolating, you know, to be or not to be. So this is a little bit ambitious task. We have been doing this for 30 years since the beginning. John Hopfield, who is a physics background and also changed to biology. He pioneered this work in 1980. So that time I went to US for study. So in 1980, he worked with Wang Lumina, together published a number of papers in this area. So basically, this is a well-known Hopfield networks. You continue times, also have discrete time version. So they implement this in simple circuits, analog circuits. Since then, there was many studies going on, basically solving all kinds of optimization problems. So this is one optimized formulation. So we have inequality constraint, equality constraint. Sometimes we separate the bound constraint as special kind of inequality constraint, because this is easier to handle. So we don't have to put this here. So depending on the object function and the constraint, we have different problems like linear programming, nonlinear programming, convex or non-convex, and also non-smooth. Actually, we also have a generalized convex problem, like a pseudo-convex inverse problem, which is a convex-like problem. And also recently we have distributionization. This Professor Shi already mentioned this, decentralized and also sometimes distributionization, same thing. And also globalization with the non-convex function, either object function or constraint. It's difficult to handle. We have a lot of such a problem in machine learning, and also data processing. And also mixed integer problem. This morning there's a speaker talk about this manufacturing from Georgia Tech. This speaker from Georgia Tech, he mentioned about the integer programming and mixed integer and combinatorial optimization problem. These problems are difficult to handle, especially for large scale problem. And also multi-object function. And there are many other problems like multi-layer optimization, which is difficult to handle. So we had some study with all these problems, but also with the multi-layer one. but the other one was not very successful, so we leave out. Okay, basically we use different design principles to design neural networks. Neural network is different from evolutionary computation. There it's more like heuristic, nature inspired. Neural networks basically designed based on the optimization theory and system theory. Okay, so basically from optimization theory we have a penalty function method, and the Lagrange methods, and duality methods, and the projection method, and the non-smooth penalty methods. This is slightly different from this one, but it's quite different in nature, in dynamic behavior. And also recently we also use the multi-agent system theory, basically, and also a swarm intelligence method to design neural networks. So besides this optimization method, we also use some, of course, Lyapunov method, and also sometimes Lassa's invariance principle to design neural networks for ensure convergence. So basically, I've been working on this for 30 years. So many problems, all the problems is easy to handle. So basically, most of the problems can be handled pretty well. Up to this point, some distributed optimization basically involved with a multi-agent or in the control community. So in neural network community, so we have different banner. So we call neural networks, but it's a special one, special dynamic system. For many complex problems, like distributed optimization and global optimization, a single model cannot accomplish the task. So we need more than one. Okay, so that's basically we need a collaboration. So that is natural, right? Because sometimes, typical task, single person cannot handle it, or single model cannot handle it. Okay, of course you can build a big giant model, like very deep neural networks, but sometimes it may not be needed, or may not be robust, or may not be accomplishable. Anyway, so we use a number of the different models, some simple one, collaborate among them without coupling, with only information sharing. That can make it work. Okay, basically, we have in distribution, Professor Shi already mentioned in depth. Well, briefly, here we are dealing with separable programming problem. From optimization point of view, the object function is separable. A constraint can be globally or locally connected. Okay, basically this problem happened a lot. In case you don't know this area, this is since 2009 or maybe earlier. There are a lot of studies, especially in control community, about this. There's some application in swarm robotics or sensor networks. So since sensor can only cover some area, with multiple sensor we can cover a big area, with connectivity to the big picture. And also, so in such application, single one cannot handle it, right? Because one sensor only can handle some area or maybe some kind of quantity variable, right? Not everything. For example, sensor could be for HP value, could be also pressure, temperature, some other things. Anyway, so we need a multi-model sensors, so handle everything. Basically, so here this problem is simple. For convex optimization, if the local object function is convex, then we can handle no problem with this is a simple one neural networks. Basically, here this is we call projection networks because here we use some kind of projection. So this is a ReLU recently we call, right? This is a ReLU in deep learning community. We use this since 90. But anyway, we call projection operator. It's basically piecewise linear activity function. Of course, here we don't have to assume the kind of smoothness of the object function. If object function is not smooth, we can have a generalized gradient. So in this case, we have the models in terms of differential inclusion. Not if this is continuous, we have different equation. Of course, some model can be discretized, then we have different equations. So this is a hidden layer handling the constraint, for example, and also connectivity. So here we have some coupling, with other networks. So, for example, AIJ will be the coefficient with coupling coefficients. This is a simple one. We actually can prove this globally convergent protocol solution. Of course, this is a continuum model. It's easier to prove, and also So here, the dual variable does not have to be reach consensus. Of course, in the resource allocation problem, which is dual problem of the primer formulation, then some of these hidden state variable vectors need to be to reach consensus, but the primer variable do not need to. Anyway, so we have a different formulation for that. Okay, so global optimization problem is much more challenging. This is a top mathematical programming problem, right? So overall, many science people dealing with this for years, for decades. Okay, so of course there are many improvement, progress has been made in the overall MS community, but not in recent years. Of course, heuristic evolutionary competition, most of the people from computer science made a big progress in recent years about globalization and also multi-object optimization with many successful stories. Okay, they design many benchmark functions to test. Okay, however, we know heuristic, they are meta-heuristic, right? And also, most of the models, they are stochastic with parameters or variables. Okay, there are problems with repeatability. Okay, so because you don't know every time you will be successful. Of course, statistically, it's would be stable. Sometimes it may not be even a feasible solution. The solution may not be feasible even because of the they handle the constraint in a simple way. Is not the same as the way in optimization theory. So actually, both neurodynamic optimization and the evolutionary optimization, they have their own pros and cons. Okay, so we can actually they're complementary. Sorry. So on one hand, neurodynamic optimization approaches are good at constraint handling, okay, and also precise local search with a proven convergence. But of course, it's vulnerable to local minima. Okay, so and because all optimization method, most of optimization method, even including the machine learning one, are gradient driven. Okay. However, evolutionary computation, they don't use gradient at all, almost no. But they're good at global search because they have different meta heuristic. But of course, they are good at weak at constraint handling and also repeatability. They cannot guarantee optimality always, right? So this is actually complementary. So basically, if we can use the meta heuristic method, for example, PSO, particle swarm intelligence, to generalize good initial condition, in initial states, then we can use a neural network to find one of the good local minima. Then we do this repeatedly, then we can find the best one. Because, most optimization problem, without prior knowledge, they start from random initial points, right? If it doesn't work, then we start again. Then all the effort was wasted. Yeah, sometimes, of course, some method build a statistic model, but it's only because we don't use this again, because many optimization problems only handle once, right? So basically, so here we propose in recent years, actually start from 1914 to 2014, 80 years ago, collaborative with neurodynamic optimization. So basically, it's kind of framework with hybrid intelligence, one bridge between the neural networks and the evolutionary computation. So we use the multiple neural networks, for example, projection neural networks, or even Hopfield neural networks. Or recently, we also use the old one Boltzmann machines. There can be different model to perform local searches. Scatter search meaning different. They start from different initial points. So they cover different area, and also a meta heuristic rule. For example, PSO rules. So used to reposition the search. Whenever they have local conversion, then they share information. Whoever find best, then we can search again. start from their own search. Okay, so this is like a brainstorming or like information sharing entities. So basically, local search and global repositioning carry out alternatively until no more improvement can be made. So actually, we can prove, in theory, this is almost true convergence. Of course, global almost true convergence to global optimal solution. Of course, depend on the complexity of the problem, and also sometimes takes depend on if the problem is very complex, we take a longer time, or we need a bigger number of population size. Okay, so basically this is a simple two-layer architecture. So this is we have a simple proof for this convergence, almost true convergence. But here, of course, in this convergence speed depend on which model we are using for local search. Of course, and also what actually the upper level we use the meta heuristic rules for repositioning to find better one. But we found this is not very sensitive. We use PSO a lot, but most of the other methods can be used. As long as they find better solution than before based on the existing local search result. So this is a simple example we use a lot by evolution competition people. Basically, this is for two-dimensional one. This is a function like this: one global minima in origin, but many pitfalls around. So if any gradient method will stuck in some local one. Here we can have a simple 5 model, 5 projection universe. So they have any of them can convert locally quickly. In microsecond, if you design temp constant small, then this is after a few iterations, they can find, everybody can find global minima. So this is a simple illustration of the power of this one. Professor Shi, earlier from Canada, we have 2 Professors Shi here. The next one also Professor Shi. Professor Shi from Canada, not Australia, talk about this global optimization, actually distributed optimization. So, of course, almost all people assume convexity, or sometimes also strong convexity. But what happens if the object function, one of them, local object function, is not convex? So that will be a problem, right? So basically we call distributed global optimization. So there, presently, there are only a few special cases. They can handle some kind of non-convexity in distribution. Okay, so basically they superimpose some strong conditions to make sure the only one global minimum. Okay, and also make some assumptions is difficult to verify, or it may not be hold. So basically, here we can use the collaboration to handle this problem. Okay, so basically, here with just recent work, we have some simple example, design another set of neural networks. So this I from 1 to 1n, with n is number of the term in the object function. So this is Laplacian matrix we used before for connection, and also here we have additional term. So this is based on the because this neural network design based on augmented Lagrange function to ensure we have a local convergence. Without this one, for non-convex object function, this neural network may not converge. Okay, so because the object function is not convex, the rest of terms are similar to the before. So this is a simple example with a term in object functions. This is a simple non-convex optimization problem. So let me illustrate point. So here we have a object function we run 100 times. Okay, so you can see if population size only one such a neural network, only one with this model. So of course we have a 43% of success. That means because here on the simple problem only 2 local minima. One is global, one is local. Okay. So this means the attraction with the basin of attraction is smaller than this one, right? Slightly smaller. Anyway, if we have 2 models work together like we did before, 97%, great success. Of course, this is if you have 3, in this case, of course, 100% always. So this means we need a friend, right? If we have some friend can share information, we can make a bigger impact. Because some information sharing. Okay, so sometimes we need a bigger population to achieve success. So that depends on the complexity of the problem. Okay, so basically, for some special class of foundation problem, for example, we call biconvex. So we can customize neural networks with only 2 instead of n could be a big integer. Okay, so this time we call duplex. Duplex means that the information exchange between the 2. But in order to ensure diversity between the 2 models, we need to do something besides the different issue points, because we actually use a 2-time scale to make this work better, avoid making same mistakes. So basically, with 2 models, we have a so-called minimal spatial complexity, right? Because 1 is definitely not enough. Right? 2 is it's necessary, but it may not be sufficient. But we have to do something. For example, 2-time scale, and also sometimes mutation operator to ensure they don't stuck in the same local minimum. So this is 2 models. These 2 models work in parallel, of course, in 2 different time scale, some faster, some slower, to ensure diversity. So this simple architecture, with one model RN1, RN2, the different, one is bigger, one is smaller. Okay, they can handle biconvex foundation problem. Of course, if the time scale have different. We also expand this one to some kind of mixed integer problem. Of course, for example, assume this is convex or biconvex in terms of x and y. Here, y is the integer. Okay, is a bipolar coding or 0-1 coding, binary coding. Okay, but x is continuous. Okay, this is of course combinatorial problem is a special case without x. Okay. Anyway, so this is can be handled by this duplex system with a 2-time scale. Okay, so we actually introduce the instrumental vector z, to handle y, because here is the integer is typical handle. Okay, we introduce z to reformulate this one as a continuous variable. Okay, basically we have a different rule to do this. Either for by unipolar coding or binary coding. Okay, so basically, essentially, we formulate the problem as a global transition problem with the x and the z. Why is z actually is the come together with x with the augmented vector x tilde. Okay, basically, so this is 2-time scale, right? 2-time scale with different time scale and 2 duplex model. So they can handle. Let me show you a simple example with only 4 variables, 3 integer, and 1 special variable. Okay, so we know the optimal solution like this. Okay, so they can be handled quickly to a few iterations find the solution. But here point is we have to make sure the time scale is sufficiently different. If they are same, sometimes works, sometimes doesn't. And sometimes even isolate, because like a couple they have same temper, they compete each other, nobody give up. Okay, so here you can see we tried the different ratio of times constant. One is the same, right? So the success rate is not 100%, of course. 2.2 is the minimum in object function. Okay, so the shaded area means all object function 100% reach the lowest point. Okay, if the difference is 1.3. Doesn't matter who is bigger, who is smaller, right? But anyway, so all less than the difference is the same is smaller or same, then success rate is lower. Okay, so that means the 2-time scale has to be sufficiently different. So without 2-time scale, sometimes we will have same mistakes. They cannot work well. Okay, anyway, so I have 20 minutes. Okay, so we did a lot of application, actually, in the last 8 years, with some non-matrix factorization, this may not be application, but it can be used for constraint clustering, and also feature selection, supervised learning, and polypolar selection. We have some projects on this, and heat page selection, sparse signal reconstruction, and also vehicle task assignment, MPC. Professor Xi mentioned this, and also recently we have also heating, ventilation, air conditioning, operation system, optimization. This is an energy engineering project. Okay. So this is maybe spend some time highlight some of this one. For example, non-negative matrix factorization. This is all topics more than 20 years. Okay, but this is biconvex factorization problem, right? For most of object function in this setting. Okay, so of course there are many applications we already know. This is nothing surprise. Okay, so basically this is a biconvex factorization. So with a biconvex object function, it's subject to non-negative constraint. So we did some study for some data sets with a few 10,000, some big, some small, with a different dimension. You can see the convergence is pretty fast. Sometimes in the beginning it's not so big, small, but later on we get smaller. This is a very different data sets. Okay, so this is a clustering result. In terms of accuracy, we can compare with other baselines. So you can see we can have 97% or 99%. Sometimes equally good. Sometimes substantially better. This is slightly better. Sometimes 9% better than the other one in terms of the accuracy. And also some other can be in terms of normalize mutual information. So the same thing we can do better. For example, here 90%. This can only 7%. Okay, these two. One of them use the Gaussian mutation operator to avoid enhance diversity. Sometimes without this diversity, they could have a same result. With this one, sometimes work better. So diversity is the key here, because we don't want to make the same mistake. Follow the wrong leader, then get the same problem. Okay, we also recently work on the sparse non-negative matrix factorization. The sparsity is very important. So this is like a lasso formulation. But here we have an integer variable, y. Y is actually not continuous. Okay. So basically, y is of course means the sparsity. So we introduce the integer, binary variable to make this one 0, 1. Okay, m is a big number, big constant. Then if y is 0, this is 0. Y is 1, this is is between the range. So this is actually, of course, with gamma is a regularization term. So we have the convergence, no problem, with a quick, even binary convergence variable. So this is a different data sets, with a different iteration, we're going down for different data sets. So this is comparison with some results. This is a pretty new work, published actually except last year. But you can see some of the method is not even feasible. So because this is two object functions, two terms. One is a relative reconstruction error, which is factorization error actually. Another one is the sparsity. They complete each other. It's conflicting. So this is a Gaussian score we define with a combined two. So you can see we are much better than others with different data sets. Okay. Also, we also work on the sparse Bayesian regression problem, which is all topics, right? So basically, we actually refer the problem in the framework of MM, majorization, minimization. We found a majorization function, then we can modify it. So majorization function looks like this. Okay, which is this looks like original regression problem with the W is unknown. We also introduced some other parameter. So here gamma and sigma had to be non-zero because they are in denominator here, and also they have to be bigger than epsilon. So the simple constraint, but object function is little bit it's non-convex, of course. Okay, this is looks like, the red one. Of course, you can see this is definitely sparse inducing. We can find better solution. It's a kind of surrogate for a Hong function, right? So this is some testing result for the 100 runs, for example, object function value. So here, actually, every time we, collaborative neurodynamic optimization, sparse Bayesian regression with two models, we run up with under lowers. But sometimes the red one, sometimes okay. Red one means only single one, but not always. Single one sometimes not good, sometimes good. It depends on initial points, right? The other one, is sometimes it's consistent lower, bigger, and bigger. Anyway, so we did two examples, actually test. One is a sparse signal reconstruction. For example, here you can see the original signal, and this is the reconstructed one, almost the same, exact same actually. Some other, of course, distorted, right? This one,
sorry, Professor Wang, we have actually 1 minute to do. Okay. Yeah.
Oh, I see. Sorry, I miscalculated.
Okay.
Okay, all right. So anyway, we did a lot of work. Okay, I have to quickly. Yeah, sorry. Okay, we also did for partial differential equation identification. So I thought I have a lot of time. Okay, sorry. Also, okay. Also, this is a sparse regularization term. All right. So I don't have time to conclude. Yeah, right. So I have. Also I have a 20 minutes. So anyway, this is a pretty good result. Also, recently we work a lot on polypolar session. Apparently, I don't have time to do this. So let me just show you some results. Recently, we compare with the different formulation. Actually, we use a conditional sharp ratio and different ratios. So for under cardinality constraint result. And also we also use distributed polypolar selection. This is the new. We use the optimization, right? So this is a distributed one. So it's good for manager distributed different side. So this is a model. We can do it pretty good. This is a in sample out sample results. Okay, I don't have time to do this. And also this is a new work founded by Hong Kong IDT. Is a heating ventilation air conditioning system. So this is a new paper we published. Sorry, I miscalculated my time. I thought I have 30 minutes. I don't want to take out too much time. My next speaker is more important than me. Okay, so let me conclude. Okay, all right. So in last half hour, I tried to convince you collaborative neurodynamic optimization is biologically and socially plausible, right? Because we use the population to head better than one. And also it have a desirable property with almost sure convergence. It's not without theory. Okay, this is a bridge between neural networks and evolution computation. Basically here we need a collaboration, which is important. Without the collaboration, example is not may not be worked. Okay, it play an instrumental role in many applications. Maybe we are doing some. Maybe you can do also. Thank you. Sorry for the run of our time. Yeah.
Okay, thank you for the wonderful talk of Professor Wang with substantial applications. So because time is limited, I can take one very quick questions from the online or here. Any questions? Okay, since there's no questions raised online, thank you, Professor Wang, again. And let's move to the next speaker.